Hello, a great welcome to Idea Statica tutorial. Myself is Jarajan P. This is tutorial number 20. Here I will demonstrate the modeling and analysis of a base ring provided below the skirt of a vertical vessel. The CHS skirt member is subjected to axial loads, shear and bending moment. The geometry of the base ring below the skirt is shown here. The bottom and top base plates are of annular shape with the top one directly welded to the skirt. Various components, namely the base plates, ribs and anchor bolts and concrete, are verified as per European code. So let us start Idea Statica tutorial number 20. Please note that the link for the playlist for all tutorials is given under the video description. So the model for the base ring that is provided below the skirt of the vessel is shown here. So I will quickly brief you the various commands and the manufacturing operations that are used for the development of this model. So let us start. So first it is a vertical skirt member. As you can see that the skirt member, it is a circular hollow section with an outside diameter of 1600 mm and a thickness of 10 mm, and is made of the material S275, and it's a vertical member, so gamma, the pitch angle is set as 90 degrees, and the model assumed for the calculation is an NVM model. Now let us go for the other manufacturing operations. The SP1, the manufacturing operation SP1, that's a stiffening plate. It is used for the generation of the annular bottom base plate. So it can be done through the manufacturing operation. So you have here the stiffening plate. So this will be the manufacturing operation that will be used for the modeling of the bottom base plate. So as you can see that the bottom base plate is having a material of S275. It's provided with a thickness of 20 mm and the shape is a circular one and the radius is 1100 mm. Okay, that's all about the bottom base plate. Now coming to the top base plate of the ring, it is generated through the stiffener manufacturing operation. So for example, if you look here, so you'll find that this is the stiffening manufacturing operation. Okay, so we have got, this is your stiffening manufacturing operation. So here as you can see that this is connected to the member M1, and it is having a material grid of S275. It is provided with a thickness of 16 mm and it is provided at a distance of 400 mm from the bottom base plate. So that is exposition is specified as 400 mm. The shape is circle and the diameter of the top ring, it is kept as 200 mm, and here the welds are provided as on both sides the fillet weld of 4 mm size. So if you see this, so let me just zoom it, so you can say that this is how the model is. So this is your bottom ring, okay, and this is the top ring, top base plate, and you can see that the top base plate, it is connected to the main skirt through the fillet welds. So that is shown here, that is on both sides. Okay, that is provided on both sides of the top ring. And now regarding the base plate, I would like to mention one more very important thing, that is the base plate is not circular, it is rather of an annular shape. So this is done through the editor. In the editor what we did is that we have applied a hole operation onto the existing base plate with a hole of diameter 1300 in it as shown here. So if you see that top view, you will find that the bottom base plate is of annular shape. So let us quickly see that. So you can see that yes. So this is the the base plate that is indicated in the orange color, and that is having an annular shape. Okay. Now coming to the stiffener, as you can see that thickness is kept as 16 mm, and it is provided with a fillet weld of 4 mm size. Now coming to the connection between the cut one manufacturing operation, This is basically used to specify the weld size connection between the bottom base plate and the vertical skirt. So you can say that here cut 1 it is used for M1, that is a vertical skirt member, and SP1, that's a bottom base plate. And you can say that it is provided with a weld, fillet weld both sides for a size. So if we just see this model, you can say that. So this is the weld operation that is performed through this cut command, that is the connection between the bottom base plate and the skirt. And you will find that the weld is provided on both sides, that is on the outer side as well as the inner side. Okay, so that is regarding the cut. Now the foundation block and the anchor boards, as usual, it is populated through or generated through the bolt grid command. So if you see the operation command, you will find that this is our bolt grid manufacturing operation. And here you'll find, you'll notice the various parameters. The first and the most important one is the fastener has to be chosen as the anchors. And here we find that the boards are to connect the base plates, that's the bottom as well as the top. So accordingly we have kept the items count as 2, and item 1 is the SP1, that's the bottom base plate, and item 2 is the top base plate, that is a stiff one. And we have selected for grade 4.6 m on boards with an anchoring length of 400 mm, and the anchor types are provided as the straight ones, right? And the radius of this ring anchor, there's a anchor ring, is kept at 925, and we have kept as per our calculations the first anchor at 11.3 degree angular positions and the balance 15 at 22.5 degrees. And regarding the foundation block, we have selected the concrete grade of C2530 with an offset of 300 mm, and the depth of the foundation is taken as 800 mm, and the shear transfer mechanism is selected to be the friction. Then coming to the rib, so the ribs, as you can see that these are all being highlighted here. These are nothing but these are used to connect the 3 components. That is, as you can see, it connects the top base plate, the bottom base plate, as well as it also gets connected to the vertical side of the skirt member as well. So you can see that it is on member M1 and it is related to SP1. Okay, and this is of member S275. The thickness is kept as 8 mm, the width is 280 mm, and the depth is 400 mm, and it is chamfered as per these dimensions. And we have provided a total of 16 ribs, and that is spread over an angular distance of 360 degrees. And here the welds we have kept as the fillet weld, that is on both sides of 4 mm size, and this fillet weld, as you can see, it is connecting the stiffener with the skirt M1 and the bottom base plate. Okay, that is our SP1. Now we need to mention the weld connection between the rib and the top base plate. This is what is done through the manufacturing operation plate cut command. So we have got 16 ribs. So accordingly 16 manufacturing operations are provided here in order to ensure the fillet weld both sides connectivity between the rib as well as the top base plate. So for example, I just want to take one P-cut one where you will find that it is used is a cut operation, and it is connected to for the one rib specified as RB1A, and it is cut by the stiffener one. So this is basically used to specify the welder connection between rib as well as the top stiffener, and all the welds are of both sided fillet weld of 4 mm size. So as you can see that the connection between the 16 ribs and the top stiffener is executed through the plate cut command or the cutoff plate manufacturing operation. Okay, so that is all regarding the various manufacturing operations and the commands used for the development of this model. Now let me just quickly introduce you the loading case that we have used. We have subjected this skirt to a vertical load of 500 kN with a shear of 75 kN and a moment of 1200 kN meter. So let us proceed for calculating this model. So this may take I think that 5 to 10 minutes time. So as you can see from the summary of the results, the analysis is performed for 100% of the loads, with the strains in the plates being at 0.2% compared to the 5% target. And there are some problems with the anchors. We will check and review what has happened. And for the welds, the concrete block, everything is all right. So let us quickly go through the verification stages for the components. So we'll just see the analysis first. So we, as expected, it is performed for 100% of the applied loads. We don't have any problem. And regarding the plates, so we find that the strain has gone up to 0.2%. So let us quickly see which are the components that are critical to us. As being seen from here, so what is problematic is what we can do is we can just sort it out. So the plastic strain, you find that is a 0.2%. It is reached on the top stiffener. This is the top stiffener plate, and this strain has reached on the tension side of it. So you will find that so as far as the 0.2% strain is concerned, the top stiffener base ring is critical for us. And we can quickly see a distribution of the plastic strains in the model. What we do is that we just press the plastic strain, and let us also try to mesh it so that we will see exactly the distribution. So this is a little bit large model, so this is taking a little bit of time. So yes, now it is all right. As expected, you can say that this is the tension side. So on the tension side, you find that just at each bolt locations, you find that the plate has undergone some kind of, the strain disturbance. That means we have a larger strain of 0.2% getting accumulated at the bolt locations as shown here, and that is also evident in this simple sketch. Okay, so this is how the strain distribution is, and we conclude that the top ring is critical for us as far as the strain is concerned. Now let us go to the anchors, and here regarding the anchors, let us quickly see. We know that there are some problems in the anchors because our stress verification has reached up to a limit of 116.1%. So we find that the maximum tension force in the anchor is of 64.5. Now quickly see whether this is good enough from the structural capacity of the bolt itself. So we just press this plus. So to see that here, yes. So the capacity of the anchor bolt, considering its yield stress, is 78 kilonewton, and this happens to be greater than the maximum load of 64.5 kilonewton. So we don't have any problem from the material of the anchor bolt. It does mean that it is some other mechanisms which is governing the failure of the anchors. So we will go through that in the detailed report in order to see what mechanism is governing the anchors, etc. Now going straight to the wells. So regarding the wells, what we find is so this is a little bit bigger model, so it is having some kind of a time problem. So let us quickly see which of the weld is critical, because in the analysis part, it is important that we critically review each and every component. And if there is a scope for keeping some sections slender or reducing the weld size, do it so that we make use of 100% of the capacity of each and every component. Now regarding the welds, what we find is that we have some 98%. So let us see. Yes, for example, these are some of the components. Yes, so this is in general connecting. Okay, yes. So let us just quickly zoom this portion off. So this is my, let's rotate. So what I do is that I will just zoom it a little bit. Okay, so we can just see which component is critical for us. Yes, so here what we see is that it is the connection of this vertical stiffeners, okay, or popularly known as the ribs, with the bottom base plate that is getting critical, as is identified by the welds. Okay, it is expected because on these ribs are subjected to a very high level of compressive forces, and the welds are subject to a high shear stresses as well. So we find that these welds are taken to a tune of 98%, and we find a similar kind of a stress utility for other ribs as well. For example, if you see this, yes, it is this rib, and we have, that means lot of the number of ribs that is on the compression side, that is creating, the welds connecting them to the base plate, very critical. So if we want, we can slightly increase it from 4 mm to 6 mm, okay, so that there is a sufficient factor of safety for the welds. Now let us quickly go to the concrete block. Before going to, yes, let me just concrete block. So let us just preview the distribution of the bearing stress below this base plate. So what we do is that we just press the stress on concrete. So we get a distribution of how the bearing stress is getting distributed below the base plate. So yes, so we find it's a distribution which is as anticipated. We find that this is the compression side. So the compression side of the concrete is getting critical. As you can see that the stress distribution is concentrated around the stiffener locations as is shown here, and we find that still we have got a sufficient margin as far as the bearing stress is concerned. It has gone only up to an 8.4%, 8.4 MPa value. So whereas we find that from the concrete block verification as per the code, you can go up to a design bearing stress of 33.5. That is leaving the factor of safety is only say 24.5%. That is very much below the 100%. So we don't have any problem as far as the bearing stress is concerned. Now the only one check that we have is the shear one. So we find that as far as the shear is concerned, the applied shear is 75 kN, and there's a design shear resistance of 20.5, keeping a utility ratio of 26.6 as shown here. This is very much less than 100%. So now, to investigate a little bit deeper into what has caused the anchor failure, let us straight away go into the report. So in the report itself, it will provide you, whatever we have discussed, okay, regarding the plastic strain distribution, regarding the bearing stress distribution, also the overall equivalent stress distribution, everything, and it also provides you how the verification for this anchors have been carried out and which mechanism is governing the their final acceptability. So let us quickly, because it's a little bit of a larger model, so creating the report may take say 10-15 seconds. So let us see it. Yes, now it is available to us. So look here, whatever we have the discussion, we can quickly preview this here also. It's a very beautiful report. Anybody can easily read it. So as expected, we find that this is the strain level. We find that yes, the strain level is getting critical on the outer stiffener plate. So that's going up to say 0.2%. And this is the distribution of the equivalent stresses. So we find that as far as the skirt material is concerned, we don't have much problem. The stresses are going only up to the tune of say 1 Newton per mm square. But regarding the stiffener plate, there's a top stiffener plate, we find that the stresses are going up. It is expected that the stresses should go up in this region because of the large tensile forces that is being transmitted to the anchor bolts. So here we find that the stresses are going up to even 275. So if we want to restrict the stresses to a level of say 200, what we can do is that we can slightly increase the thickness of the top stiffener. Now going down to the other one. So yes, these are the anchors. They are creating a not okay command. We are not comfortable with them. So let us see what is creating the problem. So as we discussed, we find that from the tensile resistance of the anchor bolt materials, we don't have any problem because capacity is 78 kilonewton, which is far more than 64.5. So it is something else that is causing the trouble, and that is clearly dictated by this failure. That is a breakout resistance. Okay, concrete breakout resistance. So it is this breakout resistance that is making the anchors a little bit critical. So as is clearly seen here. So here, how the check is performed, it is very clearly stated here. The check is performed for a group of anchors. So they, rather than an individual anchor, they are considered clubbed together, or the anchors that is coming in the tension zone, and then assumed a common failure surface in the concrete and breakout. And based on that, they computed the factor of safety. So they have considered, you can say that 1, 2, 3, 4, 5, 6, 7 anchor bolts together. And here we find that the concrete capacity is going up to the tune of 326.3 in the concrete breakout resistance. whereas the sum of the tensions in these bolts is 360.3. So here it is understood the resistance is less than 360.3. So we conclude that it is the concrete breakout resistance that is creating the trouble for us. So we can solve this issue in two ways. One way is that we just increase the offset edges of the foundation so that we have got a larger concrete area for the breakout failure. And one more thing is that all these computations are based on the assumption that no reinforcements have been provided in the pedestal, but in the pedestals for the vessels, we provide a larger amount of reinforcement, and we can include this reinforcement in the actual calculations, which provide significant improvement in the capacity of the concrete breakout resistance. And even if this do not provide us a sufficient margin, we have got some other ways like providing the reinforcement U-clips around the anchor bolts to improve their capacity. Okay, so here we find that the interaction between the shear and the tension is getting critical, and which is going to the tune of say 1.16, it's greater than 1%. So this is all about the verification of the anchors, and this is the Weld's verification. We have seen already that it is a weld that is connecting the ribs with the bottom base plate is getting critical to the tune of 98.8%. So this is all regarding a very detailed review of the results that we obtained from the Idea Statica. So I would request all of you to subscribe the channel so that a notification will be available to you as and when very interesting tutorials will be uploaded in the future. So thanks a lot, and please expect very good tutorials in future.